Assalamualaikum warahmatullahi wabarakatuh. My name is Zuhaida binti Mazlan. Today, let me introduce the topic. A line integral is one of the key concepts in vector calculus. It's about integrating a function along a curve, which can exist in different coordinate systems. In simple terms, we measure how a quantity accumulated as we move along a path. We often use line integral when the values we are studying change from point to point. For example, calculating the work done by a force along a certain path, or finding heat distribution along a wire. What is interesting is the line integrals depend on the shape of the path. Even if the path twisted or moved in 3D, the result will still change accordingly. This concept can be applied to the two of it. So the first one is scalar fit and the second one is vector fit. Thank you. Let's start with theorem 1, which is about finding the length of a curve in 2D or 3D space. This is useful when we want to know how long a path is. For example, how far a car travels on a winding road. This is the formula we use to calculate path length. Next is theorem 2, which is the scalar line integral. This is used when we want to add up something like temperature, density, or cost along a curve, when the value changes depending on where you are. This is the formula we use. We have theorem 3, which is the vector line integral. We use this when they vector fit, like a force, acting on a moving object, and we want to find out how much work is done by the force. This is the formula we use. Here we have case study 1, which is about finding the mass of a twist wire. In this scenario, we consider a wire shape like a helix commonly used in electronic device. The key point is the density of the wire is not constant if change along the length of the wire. Our objective is to calculate the total mass of the wire, and to do that, we use a scalar line integral. We use this formula. This formula allows us to integrate the density function along the curve that represents the wire. Why do we use a line integral? Because both the shape of the wire and its density vary. We need to account for these changes as we move along the curved part of the wire. Now let's look at case study 2, which is about calculating the work done by a force fit. In this scenario, a particle moves along a parabolic path through a force field. As the particle moves, the force acting on it and the direction of motion are both changing. Our objective here is to find the total work done by the force on the particle along its path. We apply this formula. This is called a line integral of a vector field.
Next, mathematical calculations for case study 1. Step 1. Find R prime t. We differentiate RT equations and we get cos t, negative sin t, and 4. Step 2. Find the magnitude of R prime t and we get cert 17. Step 3. We express rho RT since rho x, y, and z equal to 2 plus y square. We substitute y equal to cos t and we got rho t equals to 2 plus cos t square. Step 4. Write the formula for total mass m that equals to integral rho RT multiplied with magnitude R prime t dt. And we substitute the equations and we got integral 0 to 2 pi 2 plus cos square t multiplied with cert 17 dt, and we make the cert 17 as the coefficients, and integral 0 to 2 pi 2 plus cos square t dt. We separate it to the integral properties and we get cert 17 integral 0 to 2 pi 2 dt plus integral 0 to 2 pi cos square to t dt, and we use the identity to integrate cos square t and we got 1 over 2 cos 2t plus 1. We substitute in the equations equals to cert 17 integral 0 to 2 pi 2 dt plus integral 0 to 2 pi 1 over 2 cos 2t plus 1 dt, and we integrate it and we got cert 17 multiplied with 2t plus 1 over 2 multiplied with sin 2t over 2 plus t, and we solve it. We got 5 cert 17 pi that approximate to 64.7656, and the total mass of the wire is 5 cert 17 pi approximate to 64.7656. Next, for mathematical calculations for case study 2. First, we are given the vector equations RT equal to 2t, t square minus 1, 1 plus t cubed, where 0 to 2. So, we got xt equal to 2t, yt equal to t square minus 1, and zt equal to 1 plus t cubed. Step 1. Compute R prime t. we differentiate the RT equations and we got 2t and 3t square. Step 2, we compute FRT. We substitute xt, yt and zt into FRT formula and we got 2t plus t square minus 1, t power of 4 minus 2t square minus t cube and 4t square plus 2 plus 2t cube. Step 3, compute dot product FRT dot RT where we got 8t power 5 plus 10t power 4 minus 4t cube plus 8t square plus 4t minus 2, and we integrate this equation from t equal to 0 to t equal to 2 and we got 8t power of 6 over 6 plus 10t power 5 over 5 minus 4t power of 4 over 4 plus 8t cube over 3 plus 4t square over 2 minus 2t, and we solve the equations. We got 476 over 3 approximate to 158.6667. So the work done by the force fields on the particle as it moves along the path is equal to 476 over 3 approximate to 158.6667.
My name is Nurfana Fatah and we go to the maple solution or maple command. For case study 1, we are asked to find the mass of the twist wire shaped like a helix defined by the curve RT equal to vector sin t cos t and 4t. The density of the wire change along its length given the function f y z. Function f y z equal to 2 plus y squared. Using maple, we calculate the magnitude of the dr dt, dr over dt, substitute it into the mass integral with the density and evaluate from t to equal t equal to 0 to 2 pi. After computation, we got the total mass of the wire is 64.77 unit. The 3D plot shows the helical wire in the space, giving a clear visual of those shapes we integrating along. That's all from me. Thank you. Let's look at the case study 2. We are given a twist wire shaped like a helix described by the position vector, which is RT equal to 2t, t square minus 1, 1 plus t cube, which t ranging from 0 to 2. The force field acting on the partial particle is given by f function xyz equal to vector x plus y, y square minus z, x square plus 2z. Our goal is to find the work done using the line integral, which is w equal to integrate f dot dr. Using maple, we apply a vector calculus operation, calculate dr dt, substitute rt into function, and compute the product f dot dr. Finally, we integrated from t equal to 0 to 2 and got the result. Work done equal to 158.67. Next, we visualize the force field and the path of the particle. The red curve shows the helical path of the wire based on RT equal to 2 to t square minus 1, 1 plus t cube. The arrow represents the vector field from the force function, which is function fyz equal to x plus y, y square minus z, and x square plus 2z. This will help us to see how the force field interact with the wire. It confirms that the force field is changing direction and the magnitude across the space. Together, they show how the force does work along the path. That's all from me.